unpause this. Blah. All right, share screen. It doesn't look like it will. Okay, I'm frustrated. Somebody said cut and paste the. All right, so. I'm trying to figure out how to make this share the way it's supposed to. How about advanced sharing options? All right. If I cut and paste it into my, copy paste it into my document that I had that had the original equation on it, will it let me? No, it won't let me click on that, even though it's hyperlinked. What's it says? Control click. Okay, control click. Yes, okay. It only lasts like 2 minutes.
You can't see the video.
Yeah, we both
it. It doesn't show the video?
No, it wasn't showing.
All right, so it's called Imagination Land Creatures in a Vacuum. It's a YouTube video. It was originally filmed by Kent State University. Their department, they have a really nice bell jar set up, and I'm just frustrated. I'm gonna have to see if I can put the link in the useful videos set that's on the page. Let's see, there's a page that says these might be useful videos. I think I'll have to see if I can cut and paste it there, and you guys can go back and watch it later. I'm really frustrated that I can't show it through the Zoom. Okay.
Can't you just screen share while the video's on your screen?
Maybe? Do you guys see it now?
Yeah, we can see it now.
Yeah?
Yeah, we can see it. You gotta rewind it.
Let me go back to the beginning then. Okay. I thought it was really amusing. I also thought it was like really kind of shows you, because there's air pockets inside the marshmallow, as you diminish your pressure, the air pockets begin to expand. But marshmallow only has a certain, we'll call it coefficient of elasticity. So once you stretch it out, they kind of don't go back to normal. They look like they've been run over by a truck. But I thought it was a cute thing, and it fits really well because it is specifically about Boyle's Law. So that's kind of, it's like, yeah, I like that one. All right, let me see if I can go back to my notes for this. All right. More famous dead guys. The next one is called Charles' Law. We're going to keep the volume, but instead of using pressure, we're going to trade out for temperature. This is another one that starts with the theoretical version. V equals B. I have no idea why they changed the letter of the alphabet for the constant. They just do. V equals B times T. One thing that is true for all the gas laws, and we'll see this more and more as we progress through the chapter, all the gas laws have to be done in Kelvin. There's a reason for this. Okay, circle back, think about that. We did some Kelvin stuff before. If you're already in Celsius, life is easy because all you have to do is add 273. Part of the reason that they want to make sure that you are using Kelvin is you don't want negative numbers. You can't have a negative volume unless we segue into theoretical physics and talk about black holes. But otherwise, once you get 0, that's as low as you can go. You can have 0 volume if you're a photon or something like that, and you're at 0 Kelvin, but you can't have negative values. And we know that there are negative values available on the Celsius scale. Therefore, we're kind of going to ditch the Celsius scale for this particular chapter. Now, this one is a little different. This one is a direct relationship. When one goes up, the other one goes up too. Think hot air balloon. You unroll it out of the back of your pickup truck, you lay it on the field, you fire up the burner, and it puffs up. And then eventually, of course, it puffs up enough and the heat is high enough that it lifts the field. But the volume and the temperature are a key component there. Increase your temperature, increase your volume. Decrease your temperature, decrease your volume. We are not in the cold phase of the year yet. If we were doing this in, say, January, it does get moderately cold around here in the middle of the winter. If you took a balloon out of the mall and carried it out to your car and shut it up in your car and left it there and went shopping and came back 2 or 3 hours later, it would be a little on the shriveled up side because the gas inside the balloon cooled down and therefore it is not taking up as much space. If you then take it back into your house where it's warm, it would kind of puff back up to its normal amount because it's warming up again. This one is not a side-by-side type equation. This is a top and bottom equation. We've got V's over T's. When we talked about Boyle's, it said, oh, by the way, don't change the temperature. When we're doing Charles' law, the oh, by the way is don't change the pressure. You're not allowed to change 2 things at the same time and use either one of these laws. There is a way to change 2 things at one time, but you don't do that for these particular laws. And I have 2 examples. One example actually has the temperatures already in Kelvin, and the second example, they start out in Celsius. I've got 3.5 liters of gas at 305 Kelvin. warm it up a little bit, up to 360 Kelvin. What's the new volume? Again, think a little bit about your predictions. We know if you warmed it up, the volume gets bigger. So even before I do the math, I can kind of predict I really ought to come up with a bigger number than 3.5. I recommend the cross multiply method. Obviously, there is another method. You can do the full-on algebraic rearrange, but I've been doing this for a long time. People make fewer math errors usually if you use the cross multiply method. I did 3.5 times 360. That's top left hand versus bottom right hand. And then bottom left hand times top right hand gives me 305 times my V that I don't know. Multiply my 3.5 times 360. That gives me 1260. Divide by 305 so that you have your V left by itself on the right-hand side there. And my volume ends up being 4.13 liters. Yes, it is bigger than when I started. If I start with Celsius, correcting it from Celsius to Kelvin has to be your first step. If I have 5.1 liters at 120 Celsius and I shrink it to 4.3, what's my new temperature? All right, so let's go ahead and do the conversion there. 120 plus 273 gives you 393. We have 4.3 over your unknown temperature. Again, I did my cross multiply thing. That seems to be the most straightforward method. 5.1 T, technically it's T2. 4.3 times 393 gives you 1689.9 on the right-hand side. I moved my 5.1 over to the bottom and finished my division. 331.4 Kelvin or 58.4 Celsius. So think about that in terms of how you kind of get back to the idea of when one goes up, the other one goes up too. Some of the previous textbooks that I have used refer to the one that has pressures and temperatures as Gay-Lussac's law. This textbook calls it Amontons, which actually kind of surprised me. I had never heard that particular designation given to this law before. It doesn't really matter what you call it. It's still set up the same way as the Charles law. You've got pressures and temperatures and pressures and temperatures. Things to think about. Okay, if you are spray painting, and you have the spray paint can in your hand, and you are spraying the whatever. In my house, it's usually rockets. And you notice that the can is getting colder as you are spraying, because as you diminish the pressure, because there's stuff coming out of the can, it is also therefore diminishing the temperature. This is also a key feature / problem way back in the 80s when the space shuttle exploded. Their fuel tanks were under an enormous amount of pressure. And they had a batch of O-rings, basically rubber gaskets, that were supposed to control the speed at which the gaseous fuel came out of the tank and was therefore ignited. They froze. They froze and cracked. It's a weird application, but it also sort of holds true to the relevance of this particular equation. When one goes down, the other one goes down, or when one goes up, the other one goes up also. This is also why when you're done with your spray paint can, don't throw it in the fireplace or in the fire pit, because there's still a little bit of pressure left in the can. If you increase the temperature, it's going to increase the pressure. And I have this one last example that I want to go through here tonight. So I have a flask that has a fairly high pressure, 15 atmospheres. But it's at room temperature, it's at 25 degrees Celsius. If I want to decrease my pressure all the way down to regular old 1 atmosphere, what's the new temperature? All right, this one also starts in Celsius. Add your 273. So the bottom, my T1 value is 298. 15 over 298 equals 1 over T2. Do your rearrange. If I wanted to actually get this all the way down to 1 atmosphere, I have to drop it to the oh so dramatically low value of 19.87 Kelvin. We're heading toward absolute zero or outer space temperatures here. Not impossible, just possibly unlikely in a normal situation. If we go back to talking about rocket stuff again, this is something that could happen on the level of if you have rockets that are losing pressure. On last Saturday night, Wallops Island launched another, it got dubbed the space toilet mission. Okay, you can look that up if you actually don't pay attention to that sort of thing. The space station has basically a supply run that is made every certain number of months to bring more food and probably bring some of the things back to Earth. Apparently, they replaced the toilet on the space station, which I thought was kind of funny. But that was the rocket mission that happened last Saturday. And as you see it take off, actually, if you're, depending upon where you are in the Hampton Roads area, you might actually be able to see the rocket as it's launching, because once it gets up about 1/4 of a mile, you can see the burn from the bottom end of the rocket for at least 2 or 3 minutes before it actually gets too high, gets up into the orbit range. But all of these are kind of tied into gas laws. They use a mixture of gaseous fuels and liquid fuels to power the rockets these days. So it all has kind of applications to what we're doing right now. Questions either about homework that's due or gas law stuff? We will spend a fair amount of time on Thursday going over the homework and making sure I hopefully get any questions answered for you regarding the upcoming test. The test is going to be that window of starts Friday morning Friday early morning hours of midnight, and then shuts down midnight on Monday. So you basically have a 4-day chance to take the test. And I'm going to put the same 4-hour time limit on it. And it also is a lockdown browser test. That's sort of the norm of what we're all using lately. It doesn't have the video camera thing. It just, once you start, it's open book, open note. You can use, your notes, your book, your lab book. You just can't surf and you can't use each other. Questions? All right, I will see everybody on Thursday then.